Today we are going to see new article, conical pendulum. Conical pendulum. Now, before studying the conical pendulum, first we will see what is meant by simple pendulum. Simple pendulum. Simple pendulum. A small heavy sphere bob suspended by light inelastic string from a rigid support is called as simple pendulum. See here, three things are important, that is heavy spherical bob, then suspended by light inelastic string, and third one rigid support. But in practice all these three things are not there, because if the bob is heavy, then it is not point mass. Also light inelastic string and rigid support does not exist. Therefore we consider any bob suspended by any string and from a rigid support we consider, or any support, that pendulum we call it as a simple pendulum. Now we will see conical pendulum. See here, same thing like a simple pendulum. Suppose this is the bob suspended by light inelastic string, and suppose you consider in this circular track this bob moves. Suppose this angle is theta. Then conical pendulum we consider here, suppose this m is the mass of bob. Now here we consider, suppose r, this r is radius of the circular track, L is length of the string. Now conical pendulum means same thing, heavy spherical bob suspended by light elastic string from rigid support, and if it moves in horizontal circle, that means this suspension or string traces a surface of cone, then it is called as conical pendulum. Suppose you consider T is the tension in the string. Now this tension T can be resolved into two components. We consider this one. This is T cos theta, because this angle is also theta. And we consider this component T sin theta. Now suppose here weight mg acts in downward direction and centrifugal force acts away from the center, we write mr omega square. This is the centripetal force. Now T is resolved into two components. T cos theta is the vertical component, T sin theta is the horizontal component. Then T cos theta is completely balanced by weight of the bob. Therefore we write first equation, T cos theta is equal to mg. Suppose this is equation number 1. And T sin theta is the unbalanced component, or a component which pulls the bob towards center, and this is balanced by centrifugal force. We write here T sin theta is equal to mr omega square, or in the you consider in form of V, mv square upon r. Suppose this is equation number 2. Now dividing equation 2 by equation 1, we get here T sin theta upon T cos theta is equal to, we write here mv square upon r divided by mg. Here T gets cancelled, here m gets cancelled, and therefore we write here tan theta is equal to v square. v square upon rg, and therefore we get here v square is equal to rg tan theta, or v is equal to square root rg tan theta. Suppose this is equation number 3. Now we know that here velocity can be written like this: omega is equal to v upon r, and omega is equal to also 2 pi upon t, and therefore if we equate these two, then we get here 2 pi upon capital T is equal to v upon r, and therefore we get here t is equal to 2 pi r upon v. Suppose this equation number 4. Now putting equation 3, value of v from equation 3 in equation 4, we get t is equal to 2 pi, then it is r as it is, and value of v, that is rg tan theta. T is equal to 2 pi. If we take all this into square root, then we write here, instead of this r, we write r square upon rg tan theta. Now this r gets cancelled 1. Therefore, t is equal to 2 pi square root r upon g tan theta. So suppose this is equation number 5. Now, from this figure, we can write tan theta is equal to r upon h, where h, suppose L is the length of the string, then this distance we consider h is the distance. That means height of the bob from rigid support. Therefore, tan theta is equal to r upon h, and therefore t is equal to, we write here 2 pi square root of r upon g as it is, and here instead of tan theta we write r, and above h means we write here this h here, and again r gets cancelled. Therefore t is equal to 2 pi root h upon g. This is equation 6, and this equation 6 gives period of the conical pendulum. Now from figure we can write here h upon r. See here, cos theta is equal to h upon r, and therefore h is equal to r cos theta. If we put this value of h in this equation, then we can write here t is equal to 2 pi square root of, we write here h upon, instead of l, h, this r, we write l, and therefore h is equal to l cos theta, and therefore if we put this value, t equal to 2 pi root l cos theta upon g, and this equation 7, this equation 6 and equation 7 gives the period of conical pendulum. If we compare this equation 7 or 6 with period of simple pendulum can be given like this: t equal to 2 pi root l upon g. This is the equation for period of a simple pendulum. That means 2 pi under root and this 1 upon g is common in both cases. But here h or l cos theta, instead of this l, we can replace these two quantities. And this equation, suppose this equation 7 also converted into this equation of simple pendulum. If cos theta is minimum or theta nearly equal to 0, then cos theta is equal to cos 0 is equal to 1, and equation 7 can be converted easily into period of simple pendulum, t equal to 2 pi root l upon g. This is all about the conical pendulum. Understand? Okay, thank you.